So, good afternoon, everyone. So many of you already know Manabendra. Everyone has been explaining. I know Manabendra from more than last 7-8 years. I met him first in HRI where he was a postdoc there. After that, Manabendra was for 3-4 years around. He was in IISER and presently he is an assistant professor at IISER Mohali. Manobendra's research work is in diverse directions. Resources, quantum resources, coherence, non-homogeneity, entanglement theory, lots of applications, and their applications. Also, he is interested in quantum foundation. And probably today's his talk is mostly based on some this kind of aspect. Yesterday we have already listened to a talk by Devashish, some related to this similar kind. Also, another thing I want to mention, Manabendra, when we met first, it is not based on physics, rather Manabendra has some other activities, on social activities. Our first interaction is actually in that direction. After that, we have lots of discussion, debate, lots of things. So, let's hear what he's trying to tell us today.
Thank you. I think you can hear me, no? Clearly? Maybe without mic even. So, first of all, thank you, Mani. Actually, I have been here, I came here quite a few times. And it's always a pleasure. Always a pleasure. It's also very close to my home. Whenever I pass through, I always feel that I should have at least one stay here or something. This time I could manage. So, thank you once again. And so today I shall be talking about quantum-based rule, something to do with consistency and measurement differences in quantum mechanics. Once again, before I start this particular topic, these are kind of controversial things, and many scientists came up with many different approaches to resolve some of the inconsistencies. Here I have one proposition, but again, I will mostly adhere to the realm of quantum mechanics. I will not go beyond, for example, thinking about local weighted variable. Like Devashish, what he talked about is that it's a little different from here, although I will be touching upon Krausiger and paradox. My major emphasis would be to understand quantum bias rule in the most simplest scenario, that is positive measurement and unit proportions. Anyway, so let me start. So the first, so this is the outline. So the first thing I will be talking about quantum bias rule, and then try to show some simple examples that how classical Bayes rule and quantum Bayes rule could lead to two different and contradictory inferences. And then I would be applying them in two different contexts. One is this Krausiger-Renard paradox, that is also known as the extended Wigner-Penn paradox. And Hardy's setup, I won't say it's a paradox, because I will be considering everything within the realm of quantum. It's not a paradox, but the setup, and then I will come. And once again, there may be some questions while I'll be talking. So if you have something for me to clear or something, please stop me. Absolutely fine. Okay, so let me start with this Bayes rule, in particular in the classical analog of it. So consider a scenario where I have a classical bit, and then it is evolving through a stochastic process. Okay, so for example, let's say when I have 0s with some transition probability, which is also called the conditional probability, it goes to 0a. And if I have 1, essentially, it kind of probabilistically evolved to 0 and 1. For simplicity or notational, just so that you can follow, I have the initial qubit is termed as S, and the final one is 1. And the classical Bayes rule essentially says, well, let's say if I have this one, I already know from my stochastic dynamics what is the probability of finding 0a, and similarly for from 1 to 1 or 1 to 0. Bayes rule essentially gives you a tool to retrodict the process. In particular, that is useful in the context of inferences. For example, let's say from here I know that after this dynamics I get 0 and 1. Let's say I get 0a. And now if I ask, where from it? Is it from 0 or is it from 1? Obviously from here, at least from this pictorial representation, you immediately know that I cannot say deterministically from where it got it. But because as you see that this actually these two arrows are merging to 1 and 0, but coming from 0. But
the other possibility from 0 to 1 you are excluding from.
I'm just giving these simple dynamics based on that answer.
Based on that, so there is only the possibility
For the time. But let's say I get 1. Obviously, now all the things are happening probabilistically from here. But whenever I get 1, I kind of deterministically infer it has to come from 1. There is no other possibility. So how do I actually say it? Although whatever I have said it in words, how do I say it in mathematics? Your goal is essentially to find out a reproduction of this process through reproducing the conditional probability. And that is what you do using this dice. What it is, as you can understand, on the right hand side, what I have a conditional probability where S is going to A. But on the left hand side, I have A goes to S. And how do? You just have this conditional probability, you multiply with the initial probability and divide it by the final. And that is what. And in general, in order to reproduce, you need the information. See, the final one already you have. But in order to reproduce, you need to have the information about the initial. And that is where in Bayesian reproduction, you need some knowledge about the final. You need to have some information about your previous step in order to make it correct yes, or let's say correct, or let's say better inference. Now let's say I would like to extend it to the quantum domain. Well, the natural expectation is that, like, I know the classical probabilities are to be upgraded to density matrices in order to take into account all the aspects of quantum states, in particular coherences or superposition and so on and so forth. Just the probability vector is not sufficient. The similar expectation I should also have for conditional probability. I should also try to find out, at least kind of tempting me to define some kind of mathematical object which should be in the form of that. And that is what actually I'll be going to do. And once I get that, obviously now also I have to find out, like, using these two new tools, I also have to find out how to reproduce them. Obviously in that case, as you probably understood here, see, the conditional probabilities are nothing but kind of defining the dynamics, at least whenever we're talking about probabilistic evolution. In the same manner, whenever I upgrade it, I call it like other conditional state, they should be also dependent on the dynamics. No? And on the other side, whenever I reproduce, it should also represent the reproduced process, quantum process. Anyway, so this is one way. Let's say this is a prescription, but so far it looks to be the legitimate one. And let me directly go into the traditional notation that we have. Let's say I have a CPTP map, a kind of a general evolution represented by some super operator, and it takes some object, let's say a density matrix from S. And actually, an analogous causal conditional state can be defined. I will justify how it is. Just by using the Chua matrix, but up to a partial transformation. I think you can see it here, right? This is M, and here it is M. Okay? So I don't have to really say that this S prime is essentially the copy of A's and all this, because these two objects are essentially representing. For example, this is input space, this is output space. And now, if I just look at the forward process, for example, consider on the level of just transformation, I have initial state that is rho S, and I apply this map here, and I get rho. So in principle, I should be able to get it even using this conditional probability. Sorry, the conditional state. And that is defined actually in this manner. You have your conditional state, and you multiply it, although in a little different way, with your initial state, and then you trace out this one. And the multiplication, we call it a star product, and it's not actually a symmetric one. But this kind of product you have observed in many different places, for example, in Goodman fidelity, and some close relation there. But the important point is that whenever I talk about probabilities, I could just simply multiply. But for matrices, I know they may commute or not. So obviously, I have to have some kind of generalization of this multiplication so that I take into account this commuting or not commuting. But obviously, when this x and y they commute, it's nothing but just matrix. Now, the similar manner like I did given that I have a definition of causal conditional state and having some information about, let's say, this initial state, I should be able to retrodict the process like I was doing on the classical level, the Bayesian retrodiction. Like for example, if you look here very carefully, what you have, just think in this way. Let's say this is my causal conditional state. You multiply with the initial state, divide it by the final state, and then whatever you get is essentially your retrodicted process. Right? In a similar manner, this is a matrix. So that means I have to have the star multiplication of the initial state, and I have to take a star inverse of the final. That is exactly I will be doing here. See, this is my causal conditional state, then I have my initial density matrix, and this is the final.
Just one point. P lambda R is
This one.
the first one, causal conditional state.
Sure.
That is some operator on a bipartite system.
Absolutely.
And then finally,
You see, this is also.
no. An earlier line rho R is trace of R,
Yes.
trace of S, that object, bipartite density, the bipartite operator, star rho S.
Yes. So there will be an identity.
Identity is there. That's that.
Okay, so now if you consider, okay, this kind of giving you a kind of a prescription, but if I now ask what this on causal conditional state corresponding to the predicted process represent in reality on the level of operation. Actually, it turns out this causal conditional state corresponding is actually unique, corresponding to a map that is called phase recovery. So phase recovery map is a kind of a map. For example, let's say I have a quantum system, some root case, I evolve it, and possibly there is some noise. And now I say that how best I can get rid of this error and bring the state back, which is closest possible to the initial. It's like error correction in that sense. Like, and it says that the best way you can do if you come up with some map of this kind. So it is kind of saying that, well, I'm actually retrodicting, but obviously in most cases it is not possible to retrodict like inverting the operation, but you can do the best. And that turns out to be this phase recovery. And the interesting point is that, okay, let me just tell what is there. So this is like the argument that you want to apply on, like the state. This is the final one, final state. Then this is just the dual map of this one. Dual map means like that A will become K dagger and in the Gauss representation. So
this recovery map is a function of the initial state.
yes.
Means
So that is why
for every initial state I can define different.
possibly, but it may so happen that you come up with an initial state that kind of applicable to a set of
Initial states.
So that is exactly the point. See, even in the classical Bayes retrodiction, you require the information of the probability of the initial distribution. Here also you need the same argument. And actually, all these things converge to classical Bayes rule, as long as your initial, let's say, this state is diagonal in some places, and these are nothing but also commuting with the Chua matrix will commute with this this particular state. Okay, that means this object commute with this one. Whenever you have, you automatically get into this.
So, these maps each works the best in the sense that, like what sense? The trace distance between the initial state and the state is less than.
Yes, or you can say in that way. Let's say I have two initial state, let's say rho 1 and rho 2, and it goes to sigma 1 and sigma 2 with the same map. Then it says that, let's say I have relative entropy between rho 1 and rho 2, and then you go to, let's say, sigma 1 and sigma 2, and now you retrodict. It will bring you the closest possible. And obviously you can express it in terms of some resistance. It's like difference between kind of continuity, no? Difference between the relative entropy will be bounded by the fidelity of the trace distance. Got the point, no? However, I will not, as you can understand, as you also have pointed out, this is not very easy to find in general. It may not be a good recovery map for every possible input state. But in this particular talk, I will be considering a very simple setup where my operation is nothing but unity. And kind of the measurement and all these things, I will be considering a rank 1 positive. And the interesting point is that for this unitary operation, you actually don't need this information about the initials. Just because all the informations are intact in the dynamics. This is important. And with this, I will just okay. So in a sense, applying this retrodicted operation is equivalent to applying this new data. So,
Unitary is reversible. So
exactly. Yes, but you have to prove that that it does not require any prior information. So this has been proved very recently, actually, this by Francisco.
Manabendra, while you are retrodicting, you said that you will take some distance measure, right?
Yeah.
Some relative entropy distance measure such that this distance measure should be same. But for some distance measure can be defined in many ways, right? Many ways, right? So for some distance measure, this map would act well for some given initial states. For other distance measure, the other map can
So
be
in general, here we consider trace distance, which can be connected to fidelities and all these things, or push fidelity or Pullman fidelity. But don't go for Hilbert Smith distance, which is not controlled. The legitimate ones. India.
But distance is also
No,
what
it's not contracted. We'll come to that later on, but my point is trace distance, which is the most used, having a lot of options. Okay, so so I shall be restricting myself from this talk to unitary dynamics, and now let me go towards having some simple examples where I would like to show the quantum and classical Bayes rules and how they lead to different dynamics. But at the end of the day, I want to have my process retrodicted, and based on that, I would like to show. For example, what I wanted to say here, see, where I say that whenever I get 1 here, it must have come from here. That means the retrodicted conditional probability has to be 1. Right? For example, if I have 1 here, and I will see for 0, this will be 0, but for 1 it is 1. So that means this retrodicted probability essentially giving me the basis of the foundation of my reasoning, saying that yeah, it must be of this kind where I say that this 1 must have to come from here. There is not a possibility. In a similar manner, I shall also be arguing, but with the help of quantum mechanics. So here, I know there will be a little bit of this kind of bracket notations and so, but please bear with me. So let's consider a situation where I have some unitary for the time being. I just have written down this case A or B just for notational sense, but these are like unitaries. Okay? And it's a bipartite unitary, but not only that, it is kind of a conditional, control unitary. But I say, whenever it's like system apparatus kind of a charge. Whenever my system is in 0, the apparatus is not going to change. Whenever my system is in 1, my apparatus is going to change to plus. The plus is nothing but the equal superposition of 0. Well, now let me start with one thing. The thing is that let me start with a state that is like this, which is a superposition between 0. And I now attach a state of A that is in 0, and I apply this. You can immediately see whenever this is in 0, that means this is 0, nothing is going to change. Whenever this is in 1, it's going to be plus. Okay? And now, just by rearranging, I can write it down in this form. Okay? Now, the interesting point is that just look at this state. I now want to say something about, like, if I observe my 1B, obviously you may say that yes, you will be observing this particular state, but with a probability R by 2. But R by 2 means bond rule says that at least for some large number of repetition of the measurement, at least once you will get it, or with this probability, or with this frequency, you will get it. Once you get it, my argument will start. Let's say you have observed this 1B, you can immediately see from here is that because this is orthogonal, this is 0, no? Orthogonal, it will be always associated with the observation of 0. And it kind of tempts me, let me ask the question very precisely. Let's say I observe this one, then kind of it says that it must have come from this particular state. It's the same argument like here. I get one B, and I know that this can only come from here. So that means the S part should be what? There is no other possibility. No? See, what I wanted to say now, I shall be trying to argue from the classical version. Although this I have just shown for like analogy, this is not really taking a separate stochastic operation. What I'm doing, this is a conditional probability starting from this state to this, and you just take a bond rule, this transition probability of the unitary, you will immediately get this is half and the other one is half and half. This you get from bond rule, this also you get. And now if you apply your classical Bayes rule, like this one I was talking about, this will give you one. So it kind of tells me that observation of 1B kind of immediately tells me that the state of S should be 1. I mean here in this way, like the cause, if I consider this to be my effect, this to be my effect, the cause must be. This is exactly the argument in Hardy's paradigm. However, if you just apply this B dagger on this initial state here, you will immediately see your state is not that. It is not this one, it's this one. So you can at most say that this may be the cause, but with half probability. Very simple. You really don't need anything. You just have to say that, yes, how do I argue? Shall I use my classical Bayes rule? Classical Bayes rule says that yes, that whenever I find 1B, it must be 1S. But it says this is not this. However, here what I have taken like initial state to be unentangled, but my evolution is global entanglement. Let me go into the other extreme, where I shall be considering my evolution to be local, but my initial state to be. And the evolution are designed in this particular manner. These are nothing but the beam splitting operation. What I shall be doing, I will start with some entangled state, which looks into this way. Okay? And I apply this local unitary, and after some manipulation, you will see that this is exactly what happened. And now again, I will try to find out the effect of 1B. I will try to find out the cause of this effect. Right? This is exactly the question. Let's say I observe this particular thing, and as you can understand, this is orthogonal to others, right? So I observe this, and I wanted to infer the cause of it, given that this is the evolution. Once again, using just after you apply the transition probability coming from this unitaries and the probabilities of initial and final state using bond rule and so on, apply your classical Bayes rule, and it kind of says that this state must have come from here because the transition probability of the conditional probability. But again, if you just take this state here and you just take dagger of it, you will immediately see this is not the case. So when you make an inference, on which basis you will? Either you go for classical Bayes rule, or Bayes rule traditional one, or the quantum one. And it turns out to be many of these quantum, particularly on the domain of quantum, whatever the inconsistencies in terms of paradoxes are there, most using this one somehow without explicitly mentioning it. This I will come to. And now I shall guess.
So if I apply this quantum Bayes rule, then the probability of these states given that 0s1 b will be 1. The quantum Bayes rule.
See, if I get this to be my effect, and now I say what is the cause? Because this unitary is given to me, I just have to apply it. And I see that the cause must be this one, not this one. But if I use classical Bayes rule, it says that no, the cause must be this one. Right? Yeah, no?
You are now giving a prescription, right? That how to give the inference that given a state, how I can say that from where it has come. Right?
Right.
So now let's say I apply the quantum prescription.
Right.
Then that will give me that okay, that state will be the
This should be the cause, not this one.
so the probability of these states will be what? Right?
Ideally, yes. See, here, whatever the inferences I'm making, it's deterministic. Okay. Otherwise, you see this particular state is also here. So that means this is there, but we have to work. Here, all the arguments that I will be making, the deterministic ones. Now I shall go towards the Fauci-Gardner setup, and I must say that the way this paper has been written is very complicated, but I tried to simplify it, and let's see to what extent I manage. So this is introduced in this particular paper, and it starts with, let's say I will come up with steps. It starts with in the beginning that you have some initial system R, and it's a quantum system, they call it quantum coil, and it has this head and tail and so on. Okay? What it does is it actually applies some isometry. Okay? Whenever this is HR, it actually takes you, they just shows a different level, but just in this way to say that way. I attach kind of a spin here, and based on whether it is H, I don't do anything. When it is T, it just goes to plus of this it's positive. In this manner, they actually apply this isometry. And if you apply this isometry to this particular state, you will essentially have this kind of. Once again, you have to just believe me, this is supposed to be correct, that this is the state, and this again can be written down in this form given that you express this basis, this TL and HL in this manner. No, there is a bar here, and so on. So this is the second step. And in the third step, what you do, you just apply a local unitary or local isometry on the speed system. And whenever it is down, it goes to some F L O L. Previously it was L bar and O bar. Okay? And when it is up, it is just minus. Okay? And if you apply this on this particular state, you have this. Okay? So let me now come with the arguments. Although in Fauci-Gardner they talk about this, all these things are happening in different time, but it will be obvious from here that it's actually. So in this particular intermediate state, it says that it first observe OL bar. Okay? And you see OL comes only once. Everything else is orthogonal. No? So whenever OL is observed, nothing else is observed. Well, that means FL is not observed. So whenever, obviously this will come with 1/6 probability. But whenever it is observed, it is always observed with upspin. Right? I can always. The second step, I say that in the same state I'm talking about, there is no evolution. But whenever I see OL bar, I get upspin. At the same time, whenever I see upspin, I get TL bar. Again, see, up is only coming once. So argument wise, there is no problem. As far as my classical argument goes, obviously. And now, the moment I say TL bar, it can only come from here, no? There is no other possibility. And TL can only come from T, right? And at the same time, I know from my isometry itself that TR also gives me a positive X spin, right? And again, positive X spin, that is this plus this, will give me FL, right? So that is what I do, where I am. Yeah. Whenever I have this, so this is this, and whenever I have this particular spin, that is this one, because of this transformation, I will always get F. This is what it is saying, this F. So it kind of tells me that whenever I observe OL, I should observe FL. There is no other possibility. So all the arguments that I'm taking are deterministic, right? So that means on the other side, I should say that OL should never be observed. OL bar should never be observed with OL. OL bar should always be observed with FL. OL is orthogonal to FL. So that means OL bar and OL should never be observed. Right? But I see this is being observed with 1/12 probability. This is what it does. So essentially, this is the contradiction. And as somebody has said, no, it's very close to Hardy-like arguments. But the interesting point is that it starts with a single part. However, the operation is entangled. While in Hardy, you have your system state is entangled, operations of local. Anyway, so now the point is that there must be, since I have started that, I kind of promised that I should have some kind of resolution or at least a description. So let me look at this particular argument. Like whenever I observe up S, from there I kind of say this TR, and from there I say this one. No? How correct is this argument? Not just are you people managed? Are you following? I know this kind of lot of jugglings. And actually, the point is that as far as classical Bayes rule is concerned, starting from here to here is actually okay. There is no problem. Because all these classical Bayes rule apply, will always give you conditional probabilities 1, 1, 1, and this. But if you apply quantum Bayes rule, because here what you are doing, you're just doing time bound projectors and unitary operations that are all given to you. And if I just apply my quantum Bayes rule, I can immediately come to that this is not true. And actually, I think I could have simplified this one. What I actually did here, that instead of having this isometry, V1, I just divided into two. One is simply changing the level, the local isometry. Another is nothing but the control operation. And this is exactly the example I have taken in the second case, or the first case. Okay, and then you just again apply as I discussed in the example, and you will immediately see that whenever you observe this one, you take a dagger of this unitary, immediately you will see that the transition probability of the conditional probability is not. Okay? And from there, you kind of argue that yes, whenever I observe this, I do have to observe this weather. There's no problem. The important point is that the interesting point is that in these entire states, see from here to here I have written. No? How could I? Because since these are having superposition, there can be some kind of nullification, means like some kind of interference, destructive interference, like some term coming from here, some term coming from here, but they can cancel. So in quantum domain where you allow superposition, it may so happen that some of the cores are actually hidden because they get nullified. And if you take into account this one, obviously you will get this one, but this will appear with only some probability, which is not equal to 1 by 12. But if you take into account others, you will see some more contribution appears, and then at the end it sum up to. There is actually no contribution. Now I shall go towards the hardest paradox, and once again, okay, it's not paradox, the setup, and this actually got introduced somewhere early 90s. And I call it setup because here in totality I shall not go beyond the quantum understanding of quantum mechanics. Like I will consider my quantum mechanics to be non-local. I will be allowed to have a global measurement and so on. It's just a question of argument that how you proceed through the classical argument and the quantum based argument. They can give you different. So I start with this particular state. Here actually plus represents state of the system of positron, and the minus represents the system of electron, and this VU are like the orthogonal states corresponding. This kind of particle. So I've taken the same notation so that you can follow clearly. And then you apply, this is a bipartite system, you apply local wind splitting operations. And just for notational simplicity, what you do that after you apply these unitaries, here you see you have plus and minus. Minus representing a local unitary on electron, plus representing local unitary on positron. And whenever you apply, the resultant state goes to these combinations where C and D's are the upper. It's like different computational basis with the different level. Okay. And now I will have evolution, but in two different states. First, what I will be doing, let's say I shall have, this is my initial state, I apply a beam splitting operation on the positron. Here the first entry is the positron. Okay? Positron, and I get this particular state, and after a little manipulation, I get this one. also, it may so happen that I start from here, but I apply some beam splitting operation on the electron part, and I get this one. It may so happen that I first apply U plus and then I apply U minus on that, and I get this one. It's like I have an initial state, I have a final state, but there are two parts. First, I apply some beam splitting on positron and then on electron, or first I apply beam splitting on electron and then you got it. Like this is the initial, this is the final, but first I can apply some unitary on the positron part, and then the beam splitting on the electron or the vice versa. Right? And now I shall start coming with that. Let's say I do a joint measurement. Okay, and this joint measurement I see to appear with 1 by 12 probability, as you can see. Right? But let's say I observe it. And now my argument is that from here to here. For example, I know that from this state to this state, if I want to come, I have to apply some additional local unitary on the positive. No? So let's say from here to here, I did not do anything on the electron part. Right? So now let's say I have D plus D minus here, but I know that D minus part did not got touched, right, in this process from here to here. Is this clear? So that means the moment I get D plus and D minus, from here itself I say, oh, I see D minus, so this D minus must be here. And that should be there with unit probability because I did not touch it. And on the other side, I don't have any other place where D minus is. This argument actually using this classical way. Okay? And the moment you get D minus here, on the other side, D minus, because it is orthogonal, it only appears with this one. There is no other places where you have D minus. So that means finding out D minus is equivalent to finding out E plus. It kind of says that, well, from here to here, I did not do anything on the plus part. So that means my U plus should also be there with unit probability. Again, it is classical way. So it kind of says, observing this thing, kind of demanding that in my initial state, I should have U plus. The second argument. But from here to here. Now let's say I have again here I have D, the same observation, I'm just making an inference. I have D plus D minus here. Now look at from here to here, I did not do anything on the plus. This is D plus, so it should remain unaltered, right? And with unit probability. Because this D plus is only appearing here. There is no other place. Right? But the moment I see D plus here, I kind of infer this D plus also has to be there with unit probability. This is inference. Again, this D plus is observed with U minus always. That means this is also finding out D plus is equivalent to finding out U minus with unit probability. So that means finding out D plus kind of tells me that my initial state also should have U minus. U minus. Together, finding out D plus and D minus infers me through different channels though that I should be observed U plus and U minus simultaneously in my initial state. I never see that. Why? This is exactly how it's done. And once again, what I wanted to highlight here is that although I should not be saying Hardy's paradox because I did not talk about local unit, but what I wanted to say, even if you don't consider Hardy's paradox, just by classical Bayes rule you will come to this conclusion. Okay? And now I again come to saying that okay, possibly this again can be argued with the use of this quantum Bayes rule. And then, for example, let's say what the argument here. For example, you have D plus D minus 2. You say that if this is the effect, this should be the cause with unit probability. No? And I say that no, it's not true. See, here I have this state, this state, but with only half probability. Right? It's not true. And in a similar manner, the other statements also you can find immediately that, well, if I start with D plus D minus, I just take inverse of it, I will immediately see there is start. But obviously, it is coming with half probability. You have to take, also think about the contribution because here in the quantum Bayes rule, it also takes into account the superposition of causes and effects. Because these I could individually say these are my effects. But there is superposition.
So basically, I think if I've understood correctly, what you're trying to imply, see, no paradox, either Hardy or Bell's paradox, Bell's contradiction is a paradox, unless you assume the sort of philosophical aspects of local reality.
Yeah.
But the quantum-based rule runs contrary. In quantum-based rule, nothing like that is
Yeah.
okay. So quantum-based rule basically contradicts local reality. So
Or on the other side,
if you go like that, so
Or-
it's not consistent with local reality.
see, but the point is that not only that, because see, there is nothing called paradoxes. If you say paradox, that means your theoretical understanding and your experimental observations are not matching. But in this
at
particular,
the level of forget experiment will come at the level of human understanding. Experimental, of course, showed that Bell's
Violation.
inequality is violated.
Yeah.
That is one thing. So that is if you rule that out. Say that you have if you argue from the side of say quantum based, as soon as you say that you are allowed to use quantum based,
that means you accept non-local.
you are ruling out the local reality.
Absolutely.
I wouldn't say non-local, but local reality. Local
Absolutely.
reality.
Absolutely.
So
My
something like
point
that,
is perfectly correct. My only addition is that even today, in many different contexts, actually we still continue to use classical based. And here the point is that even if you just stick to classical based, there may be some contradiction even without using local, even uttering this word local
yeah,
realism.
but when we use classical basis at the back of our mind,
That's true,
of
that's
course,
true.
there is some
That's
intuition
true.
that we are respecting.
That's true.
This.
I agree.
So that is the
Yeah. So at the end of the day, this is essentially the message. That the moment you consider the quantum version of it, and then things kind of solves. And so this is what the says essentially. Thank you.
very good.
So, like, what he was asking means, can you apply this in this Bell scenario also? Means like,
I
didn't
was thinking
understand
about
that.
it, but did not find out. See, in the Bales one,
Because in Bell's argument also you are using the classical Bayes rule something.
correct.
I think there must be a way. You have to engineers still find out, but there must be a way.
I was actually thinking about it, even in JJ paradox. But the point is that, see, what you will be comparing? Their starting point is very different. Their starting point is that there is a local realistic hidden variable. Here, the moment I say quantum, I will apply quantum Bayes rule. That means I'm already denying that.
That is true.
You got the point, no?
Yeah, yeah. But you could actually couch it cleverly. Maybe. Think about it.
Yeah.
Yeah. So if I take, let's say, the very simple Starn-Kellogg experiment. Okay. So let's say I have like a beam of electrons. I measure sigma z, and I block the minus outcome. I mean the like this part, and those have the plus spin. I basically post-select those electrons, and then I measure sigma x, and then again if I measure sigma z, I will see the sum of the electrons will have minus out. So here also classical bias rule cannot explain, right? Because I already post-selected the electrons that has only plus one outcome in the z direction.
So good point you have said. Actually, here all the examples that I have taken, if you look at, it's like bipartite system. I observe one party. My argument goes like I see one party. Based on that, I want to say something on the other party. All the cases, even for Trausika here also. See, I see D minus here, or I found D plus. I know this appears to be D minus, and because I have D minus, I immediately say there has to be D plus. It's like juggling from one party to other. So for single party, see, I don't see why it has to. Well, because the classical, because at the end of the day, at the end, what we are dealing with this steering light situation. Just by observing this, it immediately kind of says what may be the other one, although it is like counterfactual, but still it goes like this. So for single party, I don't know.
Your basic before you came to hard disk setup, your argument was based on single party.
No.
Before you came to Hardy, sir.
See, all cases,
First part of your argument.
all cases, see, I observe these based on that.
No,
I say, then I say,
Probably not this, but when you define this,
the argument is without any proper mention of like whether it's single party or other, but whether there could be a contradiction or not.
So, like contextuality contradiction, I think
Possibly.
it should be possible to draw a contextuality. If you look into the
Right,
contextuality
right,
argument carefully, then I think there will be a
Possible.
Yeah. Just one more thing. So let's say if we don't take a pure state and projective measurement,
Right.
the hardy or let's say in the build type,
Right.
I have a mixed state and in general I have a pure BM. I can also get the violation.
In principle, yes.
Yes.
In principle, yes.
Then can you explain using this quantum
Quantum
bias?
based case. See, always what I wanted to say here is that, see, in both the cases, whenever you make this retrodicted argument, you require some knowledge of the prior, right? In both cases, even if you consider you don't have any knowledge, that means unbiased situation like identity, initial probability was identity. By both of the cases, still quantum one will give you a better situation. So in a sense, there you will see a difference, not in the deterministic level, but in a probability level. Like quantum one will give you some number and the classical will give you some number. You will differ. That is what. Because the reproduction is also not deterministic. Right?
So, means this rule what you have defined, quantum inference rule, means this is one way of defining it. Means like
For unitary, all of them
yeah,
converges.
that's what I'm coming to. Means like you have some justification why this is a good way. Means for these two kind of paradoxes, but here you have only unitary dynamics. There it is working, but like in case of measurement and all these things,
General measurement, general.
there this will work.
Some,
Or
I don't know, frankly speaking, because there are already some questions on how to define causal conditional, or let's say, see, you understand from here itself is that if I don't apply this one, let's say, that we were discussing, just forget this one. What is this? A joint property. No? And for quantum case, defining joint state is not very defined. Today we are talking about this POPT or something. Maybe this will have something, but I don't know. So obviously, you understand what I'm saying, Sanjay. So these confusions are still there. But for pure state, for unitary, you don't have any problem. But it's still sufficient, at least Renathan and RD are dealing with unitary states. And in particular, why I gave this title, because with this paradox, Renathan actually raised this question, whether quantum mechanics can consistently describe the use of it. Yes, in the realm of quantum mechanics itself.
I'm saying Manabendra, all his argument is using only unitary and all useful.
Yes, but inherently, if you look at that, the way they have found out the conditional probabilities, these are classical.
But you say that whatever your quantum medium rule for unitary or these things is boiled down to classical.
Yes. Sorry, sir.
For unitary, it should be.
No. For not for unitary, it boils down. Whenever these two commute. For unitary, you don't have this problem of defining, this, there are different versions. This problem.
In state dependency.
even at the level of unitary, there is some difference. That is why he is able to explain the contradiction.
The simplest.
Yeah, if you go to more complicated scenarios, then maybe again cannot say with certainty. So for
Yeah.
example, but you could still define
Give
some
the numbers.
distance measure. This is like he was asking.
Yes,
he
yes,
was asking. You
yes.
can still define in respect to those distance measures.
Yeah. So with classical base tool, it give you some number.
Some
With
fidelity,
quantum, it will give you some
with
number.
some fidelity you can
Yes.
solve. But physics-wise, I don't think
It will not give you anything.
anything.
But do you think that these things can also address this voice man level computing. So with that,
I did not do that. But on the other side, you see, here the arguments are really within quantum mechanics. Even in Weismann cavalcade, they are still going with this device independent kind of scenario. So how do you, because how do you apply it there?
Here they are doing measurement.
Here also you will be doing measurement, but here you are really using unitary or these quantum mechanical objects, in order to explain yourself. So this is, I think, one way application of this thing will be like Bayesian metrology and this kind of places where you really around real things apply something. We are thinking of something, but it is not possible.
any other question? If not, let us thank Manabendra.
Yeah.